You know, gears are pretty much the unsung heroes inside almost every machine we rely on. They're just quietly in the background, making our world turn. But what happens when they go bad? Today, we're going to dive into the science of mechanical failure, which is a surprisingly universal problem with some absolutely brilliant solutions.
So, what do your pet's food and a passenger jet have in common? I know, it sounds like the start of a bad joke, right? But the answer is actually gears. And more to the point, what happens when those gears go wrong, which can be critical and sometimes even catastrophic.
So here's what we're going to cover. First, we'll look at when gears go wrong. Then, we'll see how we can actually listen for trouble before it even starts. We'll explore how to design a perfect gear right from the beginning, check out a wild high-tech fix for broken parts, and finally, ask what a smoother, more reliable future really looks like.
First up, when gears go wrong. And we're going to look at two totally different worlds, from the factory floor all the way to the airport landing strip.
So our story starts in a place you probably wouldn't expect, a cat food factory. Imagine this. Production just keeps grinding to a halt, over and over, all because this one single gear pump keeps failing. It's a huge, expensive headache.
Now, when engineers dug in, they realized the gear itself wasn't really the root cause. It was the whole system. Turns out the cat food mixture was way too thick, the pump wasn't powerful enough, the filter was too fine, and the pipe was too narrow. All these little things added up to put a massive strain on the pump, which just wore that gear right out. It's a great example of how sometimes fixing one little gear means you actually have to fix everything around it.
Okay, so a stalled production line, that's a headache, for sure. It costs money. But the consequences of gear failure can get so much more critical, especially when we leave the factory and head for the runway.
I mean, we're talking about aviation here. The stakes are sky high, literally. The landing gear on an aircraft is an incredibly complex system, and when it fails, it's usually because of these sneaky problems, the kind of invisible threats that build up slowly over time. You've got material fatigue from constant stress, corrosion from weather, or teeny tiny cracks that grow just a little bit with every single landing.
All right, so that's the problem. But what about the solution? This brings us to a really cool idea, listening for trouble. How can we actually predict a failure before it ever happens? This is a huge shift away from just waiting around for things to break.
Think about it like this. Every single machine has its own unique hum, right? Like a constant, steady sound it makes when it's working. It's like its own little song. But the second something starts to go wrong, even something tiny, like a microscopic crack in a gear tooth, that hum, it changes. It might be a super subtle shift, one we could never hear, but it's there. And that right there, that's the whole idea behind something called vibration analysis. On enormous machines like wind turbines, engineers hook up sensors to basically listen to that hum. They create these incredibly detailed frequency time maps, which is a fancy way of saying they turn those sounds into a picture. This lets them see the absolute earliest signs of wear long before there's any danger of a real breakdown. It's like giving the machine a checkup. Okay, but what if you could stop the failure before the gear even exists? That's what we're talking about in Section 3, designing a perfect gear by creating what's known as a digital twin. Let's take the gears in a massive, heavy-duty tractor. These things are under incredible stress, and they're at risk of something called resonance. That's a really dangerous state where vibrations can amplify themselves and, well, literally shake the gear to pieces. And designing a part to avoid that is extremely difficult. Well, it used to be. Now, engineers can build a digital twin. It's a perfect computer simulation of the gear that acts exactly like the real thing. And get this, these simulations are now over 95% accurate compared to what happens in the real world. And the data backs this up big time. One study found that the error between real-world measurements and the finite element simulation, which is just a term for a super detailed computer model, is less than 5%. What that really means is engineers can test, abuse, and perfect a gear in the digital world, making sure it's flawless before a single piece of metal is ever cut.
All right, so we can design perfect gears from the get-go. But what about all the gears that are already out there, in the real world, and break? Well, that brings us to a really cool high-tech fix, rebuilding gears with lasers. You know, for the longest time, if a gear tooth broke, that was it. Game over. You had to toss the whole thing and get a new one. But what if you didn't have to replace it? What if you could just rebuild it? This is where something called laser clotting comes in.
And yeah, it sounds like it's straight out of science fiction, but it is 100% real. It's a pretty straightforward process. First, you pinpoint the broken tooth. Then, a powerful laser melts a special metal powder and applies it to the damaged spot, rebuilding the tooth one precise layer at a time until the gear is back to its original shape. And look, this isn't just some quick and dirty patch job. The results are, well, they're incredible. The hardness of the repaired tooth is practically identical to the original. And when they test its performance, it holds up just as well. It's not just fixed, it's basically remanufactured to be as good as new. So where is all of this heading? Let's look to the future. In our final section, the future is smoother. What's really next for machine reliability? All of these different technologies are pointing towards a future where our machines are just way more durable. We're seeing better designs for super complex parts, like the ones in robotic arms, and smarter ways to analyze how stress affects different shapes. There are even new sensors that can turn the gear itself into its own health monitor. And this all points to a massive shift in how we think about maintenance. We're moving away from what's called a safe life design, where you just throw a part away after a certain number of hours, to something called damage tolerance, where you actively monitor a part's health and manage it for its entire life. And that leaves us with one last, really big question to chew on. As we get better and better at predicting failure, designing against it, and even repairing it on a microscopic level, could we actually be heading towards an age of the truly unbreakable machine? Is that even possible? It's something to think about.